Add them together, I get -4. Come on, computer. -4. I need to multiply 5 and something to get 5x. Better be an x. Then when I add 5 and x together, well, these are not like terms, so I just get 5 plus x. Now the kind of the more important ones. So what numbers multiply to -36 but add up to 0? 6 and -6. What numbers multiply to -24 add up to -5? But multiply 16 add to -10. Multiply to -6 add up to 5. What is it? 6 and -1. Yep. Okay. Hopefully this is bringing back great memories for those of you that had algebra with us at the high school year. Let's bring back some. Let's look at some patterns before we go back to before I remind you of the box and diamond factoring method. There were two special patterns that we could actually encounter if we're going to factor two polynomials. We're going to factor a polynomial. One of them was called the difference of two squares. And it looked like this. If we had two perfect squares, if I had something in general, something squared minus something else squared, two perfect squares end up being subtracted, without using a box and diamond, without doing all this other stuff, a pattern this factor to really quickly was the square root of the first, square root of the second, in two sets of parentheses, one addition, one subtraction. It was one factoring pattern. So for example, if this was like, say, x squared minus, say, let's get a perfect square. How about 16? X squared minus 16 fits this pattern. It's a perfect square. Perfect square. 16 is a perfect square. X squared is certainly a perfect square. So this should factor using this special pattern in the following way. It should factor to the square root of the first. What's the square root of x squared? Just x. The square root of the second. What's the square root of 16? 4. One's plus, one's minus. Is one factoring pattern. Okay? So it's called the difference of two perfect squares. Now again, you could show that this is the same by using our box and diamond that we did last year and that we'll do eventually here for more complicated ones. But if you recognize that it's just two perfect squares, then we can go directly to this pattern. It's kind of supposed to make life easy. Another pattern was a perfect square trinomial. So if you had we had the general pattern is a squared. The general pattern is if it's in this form. So if I have perfect squares on either end, this can actually be a minus as well. If I have perfect squares on either end, then if I multiply the two square roots and doubled it, then I get the middle term. If this is where we start, then this actually factors to a perfect square, to a plus b squared. Or if this is a minus, then this could be a minus, what the notation stands for. So like a setup of this might be about x squared plus 8x plus 16. So I'm going to see, do I have perfect squares on either end? Is x squared a perfect square? Yeah. Is 16 a perfect square? Yeah. Okay, so now I want to check the middle term. Is the last one added as well? Yeah, this is addition. Then I want to check to see if I find the square root of either end. X and square root of 16 is 4. If I multiply those together and then double it, AB, 2AB, if it's x times 4 doubled, x times 4 is 4x, double is 8, 8x. Yeah, this fits this pattern. This is a perfect square trinomial. So this should factor quite readily to a plus b squared, something plus something else squared. What's going to be what's the a and the b in this case? X and 4. there are two patterns that should make life quicker. If we recognize that this is the case, then we can jump right to this. Now again, both of these, if we fall back on our old school, our box and diamond that we're going to see in just a second for ones that are not in this pattern, you should end up with the same answer. So just get, if you did the first one, you get like a 0 for the middle term. In this case, you just get x plus 4 and x plus 4, which is x plus 4 squared. Okay. There are 1, 2, 3, 4 examples down here of these perfects of these patterns. Which pattern is this? Is this a pattern? One of those two patterns. Yeah, well, it's two terms and it's subtracted, so that's hopefully a good key. Are these are two both perfect squares? Square root of x squared is 7. Is x squared of 49 is 7. So this should factor very quickly without doing any box and diamond method. One's plus, one's minus. I'd rather you not, like, are you saying, can you do like this? Yeah. I'd rather you not do that. That's very unstandard notation. You know, I want to make sure that you know that there's two different terms we multiply. So let's not do that. This one is also a perfect square. It looks a little bit different because there's something multiplied in front, but it actually fits the pattern very nicely. What's the square root of 9x squared? 3x. Square root of 9 is 3, square root of x squared is x. And square root of 64 is certainly 8. So this should factor very quickly to 3x and 8. 3x and 8. 1's plus. Okay. If there's two terms and subtraction, there's a pretty decent chance that it's going to be one of these difference of two squares. Here's three terms, a trinomial. Can we get these to fit that pattern? So the second pattern. Is it two perfect squares on the ends? Yep, r 49. Okay, if I find each of these square roots, that's r and 7. R times 7 is 7r, doubled is 14. So this does fit that perfect square trinomial pattern. We put these in parentheses. That's plus, so this is plus. It's squared. Okay. The perfect square trinomials. Let's check. Is this one going to, I put it on here, so it's probably going to fit. Let's make sure it does fit the pattern. Are there two perfect squares on the ends? Yeah. So the square root of this first one is what, 2x? Square root of this end is 3. If I multiply these and double it, do I get the middle term here? Yeah, I get 12. And then this is a minus, so here's a minus. If whatever the middle sign is going to be the sign of our perfect square. If we're not so lucky, then we're going to probably have to use our fallback is going to be our method called our box and diamond factoring method. Hopefully you remember it. If you don't recall, we'll jot down the steps for those of you that didn't have high school algebra here. You took it in the middle school. We'll jot it down real quick. Okay. So our first step, recall, is to factor out the GCF if possible. Greatest common factor. If there's anything in common amongst all of them, all three terms, then we got to factor that stuff out first. You must factor out what's in common first, if at all. If there's something in common, divide it out right in front. Do not try to just jump ahead. Make sure you factor out what's in common. Once we factor out what's the GCF, then let's see. How about we draw our box and diamond. So we'll create a diamond problem. Create a diamond problem. With what's left. We'll do it in the following fashion. I'll start with this first example here. My diamond problem, I'll start with by taking I'll multiply the ends, multiply the quadratic and the constant, and that goes in my multiply box. So negative, if the first example here, we'll do negative 55 times x squared goes on top. The adding box is the linear term, is the middle term here. So in this case, the adding spot in the diamond is, in this case, negative 6x. Once you've created your diamond problem, solve your diamond problem. So figure out what numbers multiply to negative 55, but add up to negative 6. It's, as a kind of a thought process, it's a little bit easier to play with the multiply numbers. There's a lot less pairs of whole numbers. So multiply to something, then add up to negatives, then add to something else. So we think it's the numbers that multiply negative 55? Negative 11 and positive 5. And then we want, since they need to multiply to x squared, and they need to add to one term, they better both have the same variable. When we multiplied x squared and negative 55 to get negative 55x squared.
So for like the next one, would it be
2 times 12 is 24. 24 is easy. Okay, once we've created and solved, once we solve the diamond problem, and then we'll draw a 2x2 box. And we'll fill in the 2x2 box as follows. Okay. The box part of the box and diamond, we'll draw a 2x2 box. We'll put our answers to the diamond problem in the diagonals. We'll put our original two terms, the quadratic term and the constant term, in the two spots. So first term in the first box, last term in the last box, and then fill in the missing with the answers to the diamond problem. Okay. First term, first box. Last term, last box. Answers to the diamond problem go in the other two boxes. It does not matter which way you write it. You could have flip-flopped these two, you get the same answer in the end. Once we got the box created and filled in, we're going to factor out the GCF of each row and column. So I'm going to look at each. I'll start in we'll go rows first. So what's the GCF? What's in common amongst the x squared and the negative 11x? So I'll write an x off to the left here. What's in common between 5x and negative 55? 5. What's in common amongst x squared and 5x? What's in common amongst negative 11x and negative 55? Negative 11. Your answers are written above and to the left. So our solutions then are x minus 11, x, and positive 5. Okay. Let's factor this via the box and diamond. So as I noted, this method is a lot more useful for when we have leading coefficients that aren't 1. So if we'll factor out anything in common. Is there anything in common amongst all three? Besides 1? Besides the trivial answer 1? No. 2 and there's 2 goes into 2 and 12, but not 11. 11 doesn't go in any of these besides the middle term. There's nothing in common amongst all three other than 1. So we've factored the GCF. The next step is create a diamond problem. We'll multiply the two ends. So 2z squared times 12 is 24 z squared. The middle term is the adding box, 11z. And now let's figure out what things, let's solve this diamond problem. What numbers multiply to 24z squared but add up to 11z? What are some numbers that multiply to 24? 8 and 3, wow, you just hit the nail right in the head. 8 and 3 multiply to 24. 8 plus 3 is exactly 11. So if we go 8 and 3, we want a z down here and a z squared up here, so they better each have a z. Let's create a box now from this. Draw a 2 by 2 box. Let's put our first term in the first box, our last term in the last box, and the answers to the diamond problem get fit into here. So we go like 8z and say 3z. Again, it doesn't matter what order you put the answers into the box. Now let's find some GCFs. So what's in common amongst 2z squared and 8z? 2z's. How about 3z and 12? About 2z squared and 3z. What's the largest thing in common? Just 1z. And then what's the greatest common factor between 8z and 12? 4 goes in each of those. Okay. So our solutions are 2z plus 3 and z plus 4. Get this solved by factoring. When we solve anything by factoring, we need to make sure that when we're solving by factoring, we're going to make sure that we're going to group everything on one side of the equation and set it equal to 0. So we're really we're also what's called finding the zeros of this equation. So before I try to factor this, I want to rewrite this so it's equal to 0. So I'm going to start by subtracting 14 from both sides. You get x squared minus 9x minus 14 equals 0. I think this one's unsolvable.
Really? Yeah.
Yeah, this one has no real solutions, or at least no integer solutions. Well, we can see by the following. So if we make is there anything in common amongst all three terms? No. So make a diamond problem. We'll multiply the two ends here. Negative 14x squared, negative 9x. And let's say to ourselves, is there anything, what numbers multiply to negative 14x squared but add up to negative 9? And I don't think there are. Your only real candidates are 7 and 2. But to multiply to a negative, one's got to be positive and the other's got to be negative. So you're either positive 7, negative 2, or negative 7, positive 2. Either way, you get either 5 or negative 5. You don't get negative 9. So this is going to have no integer solutions, unfortunately. Or it's just not factored. What we can do to make this problem actually solvable, as your teacher here, we're going to fix this little typo that I probably didn't want to have in there and change that to a negative 14 to begin with. So we'll add 14 to both sides. So this would be positive 14x squared. And now we can solve this. What numbers multiply to positive 14x squared but add up to negative 9x? We multiply two negatives, we get a positive. We add two negatives, we get this more negative. So if I make the executive decision to change this to a negative 14 to begin with, for you guys aren't allowed to make that choice, but I'll do it for you. Change that to negative, we'll get something we can actually solve by factoring here. So if we want to solve this box and diamond, we'll have what, x squared, 14, negative 7x, negative 2x. Find what's in common. X, general rule of, this is where, this one actually is a little bit on the tricky side. And the general rule of thumb is that if there's positive and negative, we're going to factor out what's positive. Unfortunately, we got to make sure we go back and check our answers. We check them by, this is the answer to a multiply problem. Multiplying down and across. So we'll check our answers just to be sure. X times x is x squared. X times 7 should be, the way it's written here should be positive 7x. But in the box, what the answer needs to be is negative 7x. So what's one way to make this, kind of, to change your results that should make this work? Make one of these two negative. Let's make the 7 negative. Okay? Now 7 times negative, x times negative 7 is negative 7x. I'm probably going to need to do the same thing down here, because x times 2 is positive 2x, but the answer needs to be negative. So if I do the same thing here, oh, look at, lo and behold, what's negative 7 times negative 2? Positive 4. So when we check our answers, we may need to do a minor sign editing, just to be sure. Okay, so when we factor this, we get x minus 7, x minus 2 equals 0. What are the answers then to this equation? X equals 7. You can solve each of these individually. X minus 7 equals 0. X. Yeah, so the solution will therefore be x is 7 and x equals 2 is your solution. What I have here, 4x squared, on your paper it says minus 5, negative 19x. I factored out GCF for you guys ahead of time. We're going to spend some time. 4x squared minus 5 equals negative 19x. Similar to this one, let's get this, rewrite this so it's equal to 0, and then we can factor. So add 19x's. Write it in standard form too. 4x squared plus 19x minus 5 equals now 0. Factor and solve. Okay? Factor this on your own, solve on your own. You probably want to solve it in this fashion. Take each of the two terms, set them equal to 0, and solve the little 1 or 2 step equations. Find what the values of x are on your own, and check with the part numbers. All right, let's make sure we're all on the same page here. Let's see. We make a diamond problem, folks. Out of this, since there's nothing in common amongst 4x squared, 19x, and negative 5. So let's, the multiply box, we multiply the two ends. Negative 20x squared. The middle term is the adding box. So we need to find a pair of numbers that multiply to negative 20x squared but add up to 19x. Hopefully we end up with negative 1x and 20x's. 20x to negative 1. So our box here, our 2 by 2 box should be first term, last term, and then the two solutions. And let's write what's in common. Let's see. I see a 4x. I see a negative 1. I see an x. And I see they're different signs, so we'll go plus 5. Double check just to make sure this worked. X times 4x is 4x squared. 5 times 4x is 20x. Negative 1 times x is negative 1x. Negative 1 times 5 is negative 5. So we have 4x minus 1, x plus 5. That equals 0. To finish this problem, to finish here, we'll solve each of these. I'll create little two-step equations. We have 4x minus 1 is 0, or x plus 5 is 0. Subtract 1, divide by 4. We get 1/4. Subtract 5, you get x. It's negative 5. There are your two solutions.